So let's get started with the next section in this chapter, just black propagation. And just to summarize what we saw in the last video in this entire chapter. So this in the chapter is about deep feedforward networks, also called as feedforward neural networks or multi-layer perceptrons. The MLP being the first coined term for these networks, and these gained traction in the 1990s, although it was first invented in the 1950s by some people, and that's when they call it MLP. But the actual deep learning that you all guys see was first done by Geoffrey Hinton, the godfather of AI, in the 1990s. And we, in the first section of this chapter, we saw an example of XOR, how we create a learning function of XOR, the XOR operation, and we saw the gradient based learning, the cost functions, and we saw the output units, and the fact that any output unit can be used as a middle unit, as a hidden unit that comes in the middle. And we saw how the hidden units, the different types of hidden units, the function, the default choice will be ReLU, and holistic sigmoid and hyperbolic tangent in the hidden units. Now, we also saw about lateral and how this is how softmax unit uh, is kind of similar to the lateral inhibition found in the neural cortex of the brain. So that's an interesting observation we saw, and yeah, that's what we saw. And the fourth section, we saw the universal approximation uh, theorem, universal approximation properties and depth, and the fact that the ML, basically this universal approximation says that the MLP can represent pretty much anything. It doesn't guarantee if it can learn the given data. So a representation, the guarantee of representation doesn't guarantee the fact that it will, whether it can learn it or not. So it's kind of like the Turing theorem, except instead of a computer in a general sense, this is for the multi-layer perceptrons. Uh, I'm generalizing it on a very high level, so don't take it like in an exact way. And there are other architectures as well, uh, like CNN, RNN, and transformers, which are mostly dominated today. And backpropagation is another technique that we use, and that's exactly the next section in this chapter. Now, for this section, mainly, I will be just going through the 3 blue, 1 brown video from YouTube. The textbook itself is good, obviously. This is the Bible of deep learning. But then again, for my own ease of understanding, I just referred to the 3 blue, 1 brown videos. For those of you who don't know, the 3 blue, 1 brown is one of the best channels who visualizes the mathematics, artificial intelligence, and lots of other concepts. He is also the creator of the animation packages that he has used, and which is now used by many people as well. And yeah, to check out the channel for many great visualizations. Now, so let's get to the back propagation. So, what is the back propagation? So, let's go. Let's first see the definition from the textbook. So, what it says is that the back propagation algorithm first invented by Rumelhart et al. In the 1986. They also call it as simply backprop. They said that it allows the information from the cost to then flow backwards through the network. in order to compute the gradient. So this is in order to compute the gradient. Tell us information from the cost to then flow backwards to the network. So basically, if we were to have like a network, uh, like this, let me just give a simple example. So let's say this is a network, and this is the input layer. That's the hidden layer. So we have it like that, and so once the information flows, let's call it, let's not call it anything. Once the information flows this way, it it's again brought back. So the information is also brought back and computed. The gradient is computed again, and that's kind of the high level view. And just to remind, this entire series is just a skimming series, so we just won't be going that much detail. And so let's try to visualize what this is. Uh, let me squash this, and let's say there was another hidden layer. So this is these were hidden layers. We have just squashed it into an input. So we are calling it for representation purposes. And so this is the input. This is the output layer, and so let's say so the cost function would be you have to calculate the weights 1 biases 1, weights 2 and biases 2, weights 3 biases 3. So it will have to so this weight 1 is here, and weight 2 here, 3 here. So and biases are for the same exact layers, and so what to get the desired output, what is exactly, so what do we need to so the backpropagation tells you how to minimize cost by, so like how do we make sure what's the best weights and bias values to get, so best weights and to get minimum cost function, right? So this is what backpropagation does. So and the reason why we call it backpropagation is because the information flows backwards. So in feedforward network, the information mostly flows forwards. So like it flows in this direction, it doesn't come back. So here the information comes back from the cost function. So and it goes to the first input layer, and the input layer then calculates. So and we calculate basically the what's the best value for the W and B, the weights and biases, to get the minimum cost function. Now this is done in mini batches because mini batches are just simply better. Now it's not done through like a single example. Theoretically, this back propagation is for like a single training example, but we use mini batches, and mini batches are just a randomized batches of the data, and it's just faster and more parallelized that way, and we don't lose any information because the mini batches are quite a good size. So I mean, doing it singly would require a lot of time. So mini batches is the way to go. Now the backpropagation refers to the method for computing the gradient, while another algorithm, such as stochastic gradient descent, is used to perform the learning using this gradient. So this is the backpropagation is just the method for computing the gradient, right? So and backpropagation is often misunderstood as being specific to multi-layer neural networks, but it can compute derivatives of any function. So that's that. And so basically, it computes the chain rule with a specific order of operations that that is highly efficient. So we are applying chain rule here. So go through this. Basically, uh, we need. So let's say this W is from layer L. So this is layer L. This would be layer L minus 1. This would be L minus 2. This would be L minus 3. And we get the output here. So it is Y. And so now this weights is this is the weight, and here is the should be the activation function from the previous layer, and this is the bias of current layer. So this weights bias current layer and activation from function from previous layer. These are used to calculate the uh, the Z, which is basically the cost function. Okay, so yeah, this is the let me just so we're calling it Z because we are just applying a sigma operation over whatever like all that. So that's why we are just calling it as Z, and plus yes. So now this Z is used to calculate again the activation for the current layer. Okay, and this and the Y, which is the real value, real input value, the training value, is used to calculate the real cost function for this batch, this mini batch. And as you would expect, this yeah, this and this, yeah, they are the same thing. So this would again expand to its own Z and W and B from the previous layers. So this is how basically we calculate the cost function. And this technique, the fact that we are using all this, the fact that so look at this, the weight and the bias are influencing the cost share. So that's why, and so this is kind of like the partial derivative. So the in order to calculate the cost function, you need to use the partial derivatives, uh, like uh, so of course it would be Z by partial derivative of W of L and partial derivatives of A L and Z of and so as you can see, so the we are applying the chain rule here. So the backprop is known for I mean the chain rule and backprop. So it basically uses this famous chain rule and partial derivatives. And so we call it we are saying that it's partial derivative because so I mean let's take another example from, and this is also from the 3B1 plan video. So now we are just talking about the uh, what is a partial derivative. We know what is the chain rule. The chain rule is basically that, like, I mean, if you have like a dy by, like, let's say if you call it dk, and we don't have dk, so we'll take dy by let's say we only had dx by dk, so we take dy by dx first and then dx by dk. This way the dx get cancelled, and what we're calculating is actually would be dy by dk. So and we have this value, we have this value, but we did not have this value. So that's how we get this. So this would be the chain rule. So what's partial derivative? So partial derivative happens when let's say let's take so these are the various points on a let's say like a metal bar, like a thin, like single atoms metal bar, and this is y would denote like temperature, and let's say this is the temperature. So now obviously if you were to take the 3D version of it with respect to time t, it will be smooth, right? So things will be smooth. So let's say temperature decreases or it may increase, whatever it is. The fact that we are taking the partial derivative means that uh, it's a derivative of a derivative. So in a way, uh, so the temperature. Uh, so if you were to say like the temperature, well, it does vary with time, right? The temperature does vary with time, and kind of say that this is partial derivative. So we can say this like this. We can put this like say partial derivative of temperature with respect to x squared, because well, the so so we're basically saying how this is. So this is basically same as how the temperature changes with respect to location. With respect to location, we're saying that because if you were to zoom out, uh, so again this is a partial derivative because so like in a derivative it would be just a slope, right? So this is like d dy, this is dx. We're just calculating the slope of it. No, but here this is not a slope. This is a so taking two times the x into consideration. So and so it's kind of like uh, if you say like t basically we're calling it as let's say t1 plus t3 we had average minus t2. So that's t1 to t3. Say uh, so when we're doing this, can kind of make this as like delta t2 minus delta t1. So this is a difference of a difference. So it's kind of like double difference. So this is a second difference because it's already uh, so this is a second difference, and it's why it's called a second derivative. So we can just do emphasize this is the x, and this would be delta t1, so, right? So and this would be delta t2, and let's do t1, t2, t3. So that's why the partial derivative idea comes here. And so in order to visualize it again, so like I said, let's take the 3D version of it. So let me try it again. So let's say this is like that, and this temperature, this is x, this is the time t, smart t, and we're taking dt by respect to temperature x comma t, right? So how does it vary? It's a 3D surface. So this the fact that we are calculating it partially is the reason why instead of d we call it del, this symbol which is like sigma, and it's not a sigma, it's a del. So and, so a dx by dt is just a normal derivative, but a partial derivative is when you're calculating with respect to two variables, change in t caused by that, and so say t by t, this is change in t caused by this one, and similarly partial derivative of t with respect to x would be caused by this one. So changes with respect to two things here. So changes with respect to both time and the position. Now the what it changes here, the exact value of this would be just the average of the differences. So it's the difference of the differences. That's why we are using double differences, and this is why we are calling del t by del small t equals so how temperature changes with respect to time. With respect to time depends on how it changes with respect to space. More specifically, it's proportional to the second partial derivative with respect to x. Second partial derivative, because as we saw, it's the differences of differences. And yeah, so the we're looking at neighbors and we are taking the average. That's why we are getting the double difference, and that's how we are taking. So we can kind of skip this part. I'm being a little bit slow in order to actually cover this partial derivatives. So and yeah, that's pretty much it. So what I have explained pretty much covers the actual meaning partial derivatives. So to get back to chain rule and back propagation. So yeah, we use chain rule and partial derivatives for the same reason. So because as we saw, cost function is getting influenced by the weight and biases with respect to time, and we need to take difference of differences. So and this diagram basically says everything that we need to know. So and the cost function does all the main work here. So this is and yeah, so that's pretty much it. This is the topic that I wanted to cover, and so I skimmed through the video and the 3B1 video. That's where I'm explaining this from, and this is all you need to know about live propagation. Now coming back to the textbook that we were using, the deep learning by Aaron Goodfellow. So there they also cover some other methods apart from back propagation, which are not that famous. So I'm just skipping that. So general back propagation, there's that. And back propagation also uses dynamic programming, by the way. So not only does it use, so it uses dynamic programming as well. It uses dynamic programming, the caching or the caching method. So using the table method, so that this the DP as well, DP technique. And to go through an example, and then there's history in the last part, and that's about it. So we completed the final section in this chapter.